to today's session, Advancements in Computational Fluid Dynamics. This will be presented by Mr. Vijay, who is also a lecturer and senior CFD engineer here at EIT. So I'm now going to hand things over to Vijay. You can take it away. Thanks very much.
Thank you so much, Barry, for the wonderful intro to EIT and the university and the courses that are available. So I'll just trumpet my horn a bit and talk about myself. So I have degrees in aerospace engineering with over 10 years of experience using CFD tools and software to simulate both industrial and academic problems. I hope everybody can hear me. And so I have
Yes.
an MPhil degree in engineering from University of Cambridge in the UK, and I have quite a bit of experience in capturing fluid flow phenomena using computational methods, and I have worked with the various organizations in Australia and UK. So I've worked with some of the Formula One teams. If you follow Formula One, Red Bull, Formula One team, Mercedes, and there are a lot of aerospace companies also that I've worked with and visited. Boeing, Airbus are some of them. I've done projects for consulting projects for companies like Thales, given training for employees from DSTO, which is like a defense organization here in Australia, etc. My current role is as a unit coordinator and lecturer, and I have helped develop lecture materials to teach advanced fluid dynamics and aerodynamics units for students who are pursuing masters in mechanical engineering. And I my passion is teaching these units, explaining what's the state of the art, showing them how showing students how to use the software to solve interesting problems or problems that they see around themselves using the software. And I hope I get to meet some of you in the future. So with that, I will move to the next slide. So this is the broad agenda. So for the meeting, so I can see we are over 100 attendees. So thank you again, everyone, for spending some time. And most of you, I think, are interested in seeing and finding out more about where CFD is right now and where it's going to go in the next few years. So the that's what I'll be mainly focusing on. So the advances in CFD simulation software, and uh, we are also going to look at advances in high performance computing, and there's also a increasingly important role that machine learning and artificial intelligence are playing in understanding fluid flow behavior. And then once we finish all these, we can look at some question and answers if interested. So and also if anybody has a question or so, either maybe put it in the chat and we will get to them towards the end of the session. Um, so yeah, so this is the overview of the webinar. So these are the first topic I'll be looking at is explaining the latest developments in the field of computational fluid dynamics. And after that, I'll be moving over to how high performance computing systems for CFD analysis have improved over the years. And the third main section of the webinar would be what is the role being played by machine learning and artificial intelligence in helping with understanding fluid flow phenomena. Just as an aside, this image was created by ChatGPT. I just asked it to, I just gave it a prompt, text prompt, asking it to show me some create an image visualizing the latest improvements in the area of CFD, and this is the image it created. So that's basically where it's at. You have artificial intelligence which can read what you say and read what you say and can create an image for you. Okay, so uh, uh, can you see which slide can you see? Are you having any issues with the slides?
I still see that you are on slide 6 of 27.
Okay, I moved to slide 8.
Okay. Do you want me to just move it for you?
Yeah, maybe. Maybe I need to become the presenter. Let me.
Okay.
Could you? So
you are a presenter already.
okay. So right now I'm on slide number 8.
Yeah.
So can you only see slide 6?
I move to 8. Let's see
8
when you
now.
go into the next one.
Okay.
Yeah.
I'll just move into the next one. Can you see slide 9 now?
No. Okay. I guess maybe I can do it for you. No problem.
Yeah, if you could. Thank
Okay.
you so much.
Uh,
Yeah, sorry, I'm not sure why it's not
mm.
allowing me. So if I click on sync to presenter, it's only going back to number 8. Let me just see. Okay, maybe in the interest of time, I'll request you to move to the next slide.
No problem.
Yeah. So can you see? Can everybody see slide 9? So Barry, can you see slide 9? So I'll just talk about slide 9, which
Yeah. Yeah. Everyone can
okay.
see slide
Okay, thank
8
you.
now. So then, can I move to slide 9?
Yeah, if you could move to slide 9.
Okay.
Okay. So this is a example of how CFD is being used in the aerospace and the defense industry. So when you get the PDF for this webinar, if you click on the image of the aircraft, it'll take you to the link from which most of this information is gathered, and you can use that to further your knowledge of this of where CFD is at for aerospace and defense industry. So there have been significant strides in making effective utilization of high performance computing platforms. So we have been able to create meshes having up to 13 billion cells. That's the that mesh itself would be about 40-50 gigabytes in size. It could even be more. Um, and that kind of a mesh, simulations on that kind of a mesh are going to create terabytes worth of data. So the CFD data from such a mesh can go up to 4.5, 5 terabytes. So you'll need a few hard disks to fill that up. And that is the amount of data that CFD can generate. So you need to come up with efficient ways to handle that much of a data. So there have been algorithms, compression algorithms, which have been able to bring down this 4.5 terabytes of data to about half a terabyte of data. So that's a factor of 10 reduction in the size. And you there have been also improvements in the codes that will allow solutions of 10 billion cells, which can be saved and stored on a workstation kind of architecture. So usually workstation architectures are uh, systems where computer systems which require minimal cooling. But if you look at a cluster hardware configuration, you need to house that in a separate room, ensure that the temperatures there are regulated by a air conditioning system, so you have less than 10 degrees air, so that when the air goes into the processors, it ensures that the processors remain cool. So the that these are all software side improvements to handle very large problems. And the reason we need to make these improvements is because these improvements will allow us to um, capture complex vertical interactions in aerospace and defense applications. So just to explain the picture a bit more, So these are the vertical structures that get generated when a fighter aircraft is flying at supersonic speeds. So it's these vertical structures are what result in the drag generated by the aircraft, and also they also are responsible for the lift generated by the aircraft. So if you can capture all these vertical structures accurately, you can understand and capture the lift produced by the aircraft, and that will help design the amount of payload this aircraft can carry. You can do complex maneuvers by doing transient simulations to see how the load generated is going to vary as a pilot is doing complex simulation maneuvers. So why do you need to do this in CFD? Because when you're developing a new product, it is better to be able to look at the scenario that rather than building a prototype and putting a live person in and testing it. So that's the old way of developing products. In the latest way, with the advancements in CFD, we have been able to create these scenarios virtually and do these simulations. Okay, Barry, could you go to the next slide, please? So I will. So this is so previous one was an example of how software has improved. CFD software has improved to handle complex geometries. This slide talks about how it has improved to handle complex chemical processes. I think some of you would be working in chemical processing industry. So CFD has made advancements in capturing the mixing of different fluids in industrial settings. It has made advancements in understanding how airflow patterns change within a large volume. So it could be a office complex office space or a furnace or even a workshop, etc. Similarly, complex physics like oxygen transfers, plume dispersion. So, for example, there's a pollutant being released by a chemical plant. You want to see whether it is going to be diverted onto residential buildings, because then that is hazardous gases that people would potentially inhale. So these kinds of things you can now model in CFD, look at these scenarios, and then come up with effective mitigation measures. Okay, so the key improvements or advantages of using CFD in the chemical processes industry are: we can maximize the value of existing facilities and processes. For example, this plume dispersion problem, if we could instead of shutting down the plant, we can come up with solutions which will divert the plume away from residential areas, for example. So that is going to save a lot of litigation and hassle. So CFD is very important in that way. Then these mixing reactors. Usually, when you're developing a product, you test or develop the product on a model scale. So if you're creating a new chemical for a drug, or you want to create a drug in a new fashion, you you do experiments on a test scale, model scale, and once you get a formula that works on model scale, you need to scale it up to production scale. So you don't go ahead building a reactor, because from the model scale to the real scale, the mixing time scales, etc., can change. And that's where you do CFD simulations to fine tune those parameters. And then once you know that, yes, it's giving the right results, then you go and create a prototype, and because otherwise it'll get too costly. So, and that kind of leans into that plan and efficient scale up or scale out strategy. So you find an alternative way to produce a drug, and then you want to commercialize it. So you need CFD for these kinds of things. And greenfield designs, you can access and improve the performance by you're essentially creating this virtual environment and looking at how the fluids would interact in this virtual environment, and then use that to actually improve on the existing or help your design choices. Okay. There's also quite a bit of CFD being involved in sustainability industry. So solar, I'll touch upon this again, but wind energy, solar energy are two of the main um, renewable sources of energy right now. So wind turbines, you need a lot of CFD to design the shape of those fans or the arms of the wind turbine, so that it is as efficient as possible, and it can extract as much energy as possible and then convert it into electricity. Solar farms, um, they are they are basically very susceptible to strong wind events. So that's where the CFD is being used in these sustainability goals. So I think these are a few improvements. So all this happens through the development and inclusion of new models. So a lot of research is being conducted in universities all across the world. A lot of researchers keep coming up with new models to more efficiently predict certain processes. And then a few years, once these models get peer reviewed and they get accepted by others in the in the same field, they get incorporated in commercial CFD codes, and industrialists or simulation experts in industry can use these. So this is how year on year the capabilities of the software are improving in tackling a more wider variety of problems. So Barry, if you could go to the next slide. So this is an example of how biomedical industry is using CFD simulations. So these are CFD simulations conducted for a heart, and what is the advantage of doing this is it can quantify the loads exerted on the cardiovascular system due to blood flow. So and it can these simulations can provide useful insights to physicians to recognize the onset of any heart related issues. um, and there's a lot of research work and simulation work that is going on all across the world right now in this industry. Then we also have other applications of CFD in the biomedical industry. So there have been quite a few studies which have been done, which visualize the drug delivery through a respiratory system, and this can help in developing a new class of medicine. So nobody wants to swallow big tablets. If there's a way of injecting the same medicine in the form of a powder, then maybe it's a bit easier to get into the body, and maybe it's a bit more efficient as well. So CFD is used to track uh, the the travel of these small microparticles containing the drugs into a respiratory system, and there's a lot of CFD being done on that, and a lot of, hopefully it will lead to the development of a new class of medicines. And we've just come out of these. I mean, COVID is in our rear view mirror, but there was a significant uptick in CFD software in understanding how airborne diseases can spread in indoor environments. So you might have seen quite a few, if you are on LinkedIn or were on LinkedIn during COVID times, you might have seen quite a few simulations where people simulated somebody sneezing, the droplets getting released, and then how they would spread because of the HVAC system and all that, and then trying to come up with barriers and guidelines so that the spread of these droplets is minimized. So CFD is still being used for understanding the spread of other airborne diseases. So Barry, could you move to the next slide, please? Thank you. So this slide talks about some of the latest developments in using CFD in the field of sports. So sports is very competitive, and any advantage you can get over competition is thoroughly investigated. So and most of our sports involve moving in one type of the fluid or another. So this is an example of cycling. So if you there's a very famous cycle race called Tour de France that happens in June, July, where cyclists have to travel about 3,500 kilometers. And then whoever covers this distance first is crowned the champion. Quite a few riders start, and you will see that every stage there are a few who just ride off into the distance, but a majority will actually stick together in a bunch, and then only towards the end they would somebody from that bunch would try to break and then try to win the stage. So that bunch is generally called the peloton. And so here is an example of CFD simulations done on a peloton. So each of these dots you see is a rider of who is riding, and depending on the formation of the peloton, the different riders will experience different levels of drag. So somebody who is in the interior regions of the peloton will experience less drag, which means they can conserve more of their energy until the later stages where they can then break away and then try to win the race on their own. So this was a study done in a university in Europe where they looked at various configurations and conducted simulations containing with hundreds of millions of cells to identify which are the most optimum positions for riders in a peloton. Okay, so very fascinating. These simulations themselves will take a few days to run, and then analyzing the results will again take a few weeks to come up with the results. So, lot of cycling companies who want to participate in these events will make use of CFD to ensure that their riders are riding in the optimum position to minimize their drag, and they're also they juggle to place them in the right position so that they can conserve their energy until the time comes. Other sports like Formula One and other racing organizations extensively use CFD simulations to improve the performance of cars and bikes and so on. So again, you can click on um, this link, and then it will take you to the paper which gives more information on these CFD simulations of the Tour de France peloton. Barry, could you move to the next slide, please? Thank you. So this is an example of how CFD is used in the power generation industry. So as I briefly alluded before, renewable energy is key to ensure we are building and maintaining an environmentally sustainable future. So these wind turbines, they create very large wakes, and we need these high fidelity simulations to help visualize these wakes. And the way this simulation helps is it helps you in identifying the size of the wake so that any downstream wind turbine is not placed in the wake. So this image, what it's showing is how there's a very neat flow that is coming and interact and as the turbine, and it basically, when the flow moves over the surface of this wind turbine, it is going to create pressures, differential pressures on the top surface and the bottom surface of the wind turbine. And that differential pressure will create a moment about the center of rotation, which is the center of rotation in the middle. And that torque so once these blades of the wind turbine rotate, they will turn a dynamo which will convert this energy into electricity, and then that is fed off into the grid. So the byproduct of all this is whatever air goes goes through the wind turbine becomes disturbed, which means its energy is absorbed. So if you place another wind turbine right behind it, like as if they are in a line, the second wind turbine will actually see this low energy air, and it can't extract any more energy from there, or its efficiency will be significantly reduced. So you can do these high fidelity CFD simulations, identify the extent of the wake, and ensure that the next turbine, the downstream wind turbine you place, is not in this wake. And it also gives you a good idea of when this wake will dissipate, and the energy is again high enough for another wind turbine to be placed. So these are like again very large simulations which run into hundreds of millions of cells and require weeks and weeks of running and understanding the results. So similarly, solar farms are also very sensitive to wind loads. So any gusty wind, you can. These solar farms are mainly thin wafer-like structures, which will generate energy because of sunlight falling on them. Because they are very thin, they are susceptible to strong winds. So if they are aligned in a way that there is a large pressure differential when wind is blowing over them, you can see that these solar panels will fail. So they'll basically snap into two, and that's quite a bit of energy. I mean, investment loss to anybody who's running the wind farm. So it'll mean that they'll have to go back and either replace that panel. There's also loss in the amount of energy that or electricity that that panel is creating. So that's a direct financial loss. You have to replace it at your own cost. All that. So understanding CFD or using CFD to understand behavior of these solar panels to strong winds is a up and coming area of research. Okay. Could you go to the next slide, please, Barry? So this talks about the latest developments in using CFD in the building industry. So as we know, we are living in a rapidly warming planet, which would lead to stronger cyclonic events in the near future. We are actually seeing that already, where either the hurricanes are stronger or they are occurring earlier than before, and then they are leading to more widespread widespread flooding in regions which were previously not experiencing that flooding. And the reason is hotter air can hold more moisture. So if the global temperatures increase, more moisture can be accumulated in the atmosphere, and then when it rains, it will start pouring, and it will affect. It'll lead to a lot of effects, and we are probably seeing that everywhere. So because stronger winds and the higher wind loads will become a norm in the future, buildings need to be designed to withstand these higher loads. But then you can say, oh yeah, if this has to withstand higher loads, you just make the walls thicker and the concrete more use more concrete. But the problem with that is more using more material would lead to more costs, and it will also lead to more emissions themselves. So if you need to create more concrete, there's more CO2 generated in the process. So you need to come up with more efficient structures which withstand stronger wind loads without really doubling in the amount of materials required to build them. So in that, a lot of research is being done to make use of CFD simulation methodologies to capture structural loads on buildings and quantify their dynamic response to strong wind events. So when I mean dynamic response, so imagine you have can you all see my mouse? Barry, could you see my mouse or no?
No, I can. Let me see. No.
Okay, if you can't, I can't. Let me see.
Okay.
Okay, maybe I can't. So essentially, I wanted to point to that small black and white picture in the bottom right corner of this of the picture on the right. So that's an. Uh, Let me see. Uh, I'm just checking if I can find. Actually, there's a take control option. I've clicked on take control, Berry. Maybe. Okay.
Yeah. Okay. Yeah. It's now showing.
Okay. Okay. Sorry. Go back. Okay, so if you can see my mouse,
Yes.
so yeah, so that one, that's an example of a test building, and what we are looking at is how the loads on this building are changing as the height changes. And what you can do is you can make use of this information to ensure that you have extra padding only where you need it, and you can run this building through a scenario of so there's what is called as a wind code, which will give guidelines on what type of winds a structure should safely withstand. And you can set up a CFD simulation to represent this building in that same in a similar situation, like as if there's a strong wind event passing through, and then this building is caught up in that. It should not. It should retain its structural integrity. So that's the idea of this, and and lot of ongoing research is being done to make use of these CFD simulation methodologies. So the equations are the same, but the computational requirements to capturing these kinds of dynamic responses to strong wind events is still um, it needs more computational power, which I will allude to in the next few slides. So the computational power is what's limiting us. The models are there, the equations are there, but we need to be able to get these things done in like a 6 week time frame, not a 6 month time frame, because builders will not wait for 6 months to understand the effects of their design to wind loads. They would want it much faster because they can't. They want to build something within a 2-3 year time frame, and if analysis itself takes 6 months, they are just playing catch up all the time. Okay, so this slide talks about the advancements in CFD over the last few years, advancements in computations or computational power in the last few years. And on the right hand side axis, it kind of talks about how it is relative to the brain power of a simplistic animal. Um, this is maybe before AI became really powerful, but I think it's still worth having. So CFD simulations are extremely hungry for computational power. Other than deep learning algorithms, I can't find many examples where software codes are so hungry on computational resources. So as the number of chips that we can squeeze in on a transistor um, is doubling every 2-3 years, along with higher clock speeds. It means that every 5 years, the the speed with which we can do computational simulations is roughly doubling every 5 years. And on top of that, there have been improvements to ensure more and more CPUs can talk to each other efficiently. So when I was starting off with CFD, we were doing simulations on 6 to 10 cores at the most. Um, and now I do simulations on 128 to 256 cores. And that's just how on a day-to-day basis, and that's because of improvements in both the processor speed and the number of calculations it can do per second, and also number of processors that can efficiently talk together. That's called that's how the clusters are built. So and also their efficiency is gone up. So to do the same simulation in the last 5 years, the the power requirements have probably become half or lesser. Okay, so the all the examples I described before, you need you need faster processes that will help capture all these complex interactions in between fluids, and techniques like large eddy simulations and other scale resolving simulations are the way to go to capture these complex interactions, and that's why we need ever more higher computational power. Okay, so um, thankfully we have had another revolution in um, increasing the computational power that is available to us. So CPUs, which are the central processing units, like your Intel and AMD processors, they have been eclipsed by graphical processing units or GPUs, which are being developed by companies like NVIDIA and AMD, and they have become the go-to options for compute intensive processes. So this is driven largely through data science and machine learning and artificial intelligence algorithms. But CFD, because it is equally hungry for computational resources, has been able to leverage the GPUs, which are highly specialized in these matrix multiplications. So I'm sure quite a few of you must have done mathematics where you've gone through matrix multiplications, and CFD codes are essentially a very big matrix multiplication, which is conducted to come up with a flow field that satisfies the governing equations. GPUs are perfect for these kinds of work. So only thing is you need to rewrite the CFD codes to leverage these GPUs. But if you do that, it can result in 10 times faster simulations. In some cases, they can even go up to 100 times faster. So as I was saying, we can't. When I said building or clients can't wait for 6 months to get a result, but if you can get them a result in 6 weeks or even a week, then um, they'll be paying for getting that information in a 1 week turnaround time. Okay, so that's one of the reasons why this is the latest research area for a lot of commercial CFD software providers. And maybe in the future, we'll be seeing simulations that run on thousands of GPU cards. Um, NVIDIA, I'm not sure how many of you follow NVIDIA, but or just American companies and their fortunes in general. But NVIDIA is a company which has, in the last 3-4 years, its value has gone up more than 10, 20 times. So if you had any NVIDIA stock 5 years ago and you didn't sell it, your stock has gone up 10, 20 times. So and the reason is because these GPUs have given an avenue for getting a step change or step improvement in the or reduction in the computational time required to do CFD or deep learning algorithms. So what does all this mean? um, Improvements in CPU and GPU architecture are going to help conduct more LES simulations. Again, you can click on this link and it will take you to the website of a French university who have done a simulation, a full scale simulation of flow through a gas turbine engine. Um, I put this slide because I have a personal story to share. Um, where I remember sitting in my first job. I remember sitting in a talk given by a senior researcher from that organization, where they tried to do a full-scale CFD simulation through an engine, and they realized that they're not there yet in doing that. So this was between 2006 and 2008, around 2007. So that's about 18 years ago. But in the space of 18 years, advancements in both software and hardware have allowed researchers to do this kind of a simulation. And so what you will see here is um, these high fidelity like images are large eddy simulations, which will resolve all the large time scales of the flow. So these are all the large vortices that get generated when the flow goes through a gas turbine engine, and these are all simulations that change with time, and they require millions of cells, and then they generate terabytes of data which you need to store and analyze properly to actually get the information that is going to help the product to improve. So just doing simulation for looking at some pictures is not the goal in industry. You use the simulation data to give your client important information on how to improve the performance of their product or solve a problem that needed the CFD simulation in the first place. So, so that's the first two sections where I first talked about software improvement um, in handling more complex geometry and more complex physics. Then we talked about how the computers themselves, the CPUs and GPUs, have improved to allow more complex simulations. Now, the third section is a new frontier that has opened up in the last 4 or 5 years. So, artificial intelligence has taken over quite a bit of um, it has gotten embedded deeply within our day-to-day lives, and all of this is through various deep learning algorithms that have been developed all over the world. If you get to the core of it, the computations required to run these deep learning algorithms and the same are very similar to the computations required to run CFD solvers. So people or researchers in who are working in the CFD field have recognized this and tried to come up with novel ways of utilizing this new field of artificial intelligence to augment the CFD data that is being generated. Okay, so CFD, so AI algorithms require a lot of data. For example, if you want to develop a self-driving car, you need to give it um, hours or months of footage, which helps it identify various obstacles that can be encountered when a car is driving on a busy road, and then it will be able to understand and come up with ways of reacting to those obstacles. Similarly, and it will need lots of data. And CFD is one software or one area where you can generate huge amounts of data. As I've just mentioned before, you do an LES simulation, you have terabytes worth of data. You can then feed this data into AI algorithms and allow them to find patterns. And you can then capture these patterns and then utilize them to flesh out um, data which is more sparse. So, for example, um, here is an example where you take a flow across a cylinder or just flow in a channel and send it to an AI algorithm. And what it can do is it can create structures, 3D turbulent structures that will mimic a 3D problem. And what is the advantage of that? If you have an experimental data where usually the data is available at select points, you can use this machine learning tool or AI tool to flesh that discrete data information from an experiment into a full-fledged 3D turbulent flow field. And the key thing is be reasonably it will reasonably satisfy the governing equations. So that's the um, main advantage of this kind of this avenue. So it'll allow closer cooperation between experimentalists and simulation engineers. So this is one way that machine learning is being used. This is another very interesting area of research for uh, lecturers and professors in universities all across the world. So this is what is called as a physics involved neural network. So I'm not sure how many of you are aware of what a neural network is. That's at the heart of all the artificial intelligence programs. So it takes in a bunch of inputs and then learns some parameters or weights in this neural network so that you get the outputs that you generate, that you desire. So previously I showed you a picture where I asked it to create an image that represents the latest developments in CFD. So that was a text input, and then it will create an image based on the text input. So that was an example of a neural network. It's the same if you use something like ChatGPT. You ask it a question, you give it text, you say, "Oh, write me a letter. Maybe write me a letter to get me admitted in EIT," and it will basically, and you can give it your resume. It will go through the resumes. This is all text input, and then come up with a letter which will highlight your past experience and then explain, or it will provide some scenarios to showcase how you will use that experience to improve to be successful in AIT. Okay, so eh, that's an example of a neural network. Same thing can be used to where you add another layer to the neural network where you incorporate the physics. So in, for example, you have this standard neural network, but you have another term where you try to satisfy the continuity equation or momentum equation or even the energy equation, and you come up with, you calculate these weights so that these equations are also satisfied. So what that will do is, again, it will help you create a more 3D visualized flow field based on which will, based on extrapolating on some certain data points. So this is again a rapidly evolving area of research. um, in a couple of years it might you might find a breakthrough where it might, you might create a model which will supersede all the existing CFD codes. That could happen, just like ChatGPT has mostly superseded the chat or Google searches and etc. Somebody, if they, instead of finding the answer on Google search, you just ask this question to ChatGPT, and it will find the answer for you and give it to you in a easily digestible manner. So it will go through all the search results and give you the most relevant. So hopefully, advances in this machine learning will lead to similar advances for CFD. So this is, I think, the one of the last slides, and we are close to finishing as well in terms of time allocated. So we have another avenue for machine learning, which is called surrogate models. So surrogate models are simplified approximations of complex fluid phenomena or fluid models. So what it does is it maps input data to output where the relationship is very complex or unknown, and then it will find patterns between the connections between the inputs and the outputs, and with these patterns it's going to be able to um, uh, for example, predict aerodynamic quantities of interest, such as pressure distribution, lift, and drag, based on a velocity information. So, an example is usually when you're doing experiments, you either capture the velocity information or a pressure information at a given point. And suppose you're in your experimental data, you measured velocities, but you don't have pressures. If you have these kinds of surrogate models, what you can do is you can feed in this velocity information and come up with a pressure field that will satisfy the governing equations. Um, and so it'll give you a physically valid pressure field without needing to rerun the experiment or do a CFD analysis. So these kind of surrogate models can be very useful for experimentalists and also for various researchers. Okay, so you can have these models which can be trained for a particular class of problems. Suppose you are just doing airfoil research, then you can train it on airfoils. If you're doing flow around bluff bodies, then you can train it on cylinders, etc. Again, this is a very rapidly evolving area of research. So all of these, when you get the PDFs, each of these would have a link to the article from which I gathered this information. I've tried to present all this in a very compressed time frame, but if you have enough time, you feel free to explore each of these articles in more detail. So, so this kind of brings me to an end to the webinar, where I've briefly discussed the latest developments in the field of computational fluid dynamics. So we see how CFD software is improving its capabilities in and trying to keep pace with high performance computing systems for analyzing complex systems. We've also looked at various exciting avenues of research that have been opened up by the development of machine learning and artificial intelligence algorithms. So I think that brings me to the end of this session. I think we have 4 or 5 minutes. Um, if you would like to ask any questions, so I think I'll just answer this question. I think it's Mushahid. Um, so do let me know what your question is, or maybe if you can paste it in the chat. If you can paste it in the chat, I will look at this. Okay, so one of the questions is, what have been some of the most interesting projects I've worked on? Um, I've One of the most important interesting projects I've worked on is I've done a CFD simulation trying to understand how the airflow patterns evolve when a train is coming into an underground tunnel. So if you have an underground uh, tunnel in a metro system, whenever a train is entering, it will push air through all the various um, walkways, and you want to ensure that the velocities created do not cause people's hats or papers or phones to fly away. So that was one of the interesting projects. More recently, I've done a simulation simulating a part of Sydney and looking at how windy it would get in certain regions. Next question. I think certificate of attendance. I think if you've provided your email, you would get a certificate of attendance in a few days. Um, and if you've not, maybe email Barry, or sorry, Barry, and he might be able to help you out with that. What's the most efficient CFD software for renewable energy technologies? I would say most commercial software would be able to tackle these. It's more on a user skill rather than the software, um, because right now softwares have evolved so that they can solve these kinds of problems. The bottlenecks would be how skilled a person is in using the software, and how accurately the inputs provided will represent the real case scenario, and also the resources that are available to them. So if you have a laptop, it's very difficult to look at flow past the wind turbine that I showed you in one of the slides. That requires at least 200, like a cluster with 200 CPUs running for a week or so to get those results. Okay. And then, okay, what are the first things that might go wrong? Um, User inputs. So if you give incorrect boundary conditions, or you choose incorrect turbulence models or other models, then you'll not get good results. Um, Sometimes the simulation itself will, and also meshing is an important part. If your mesh is not good quality, the equations will not be able to solve properly, and you'll not get a result. This actually
Uh,
happened to me yesterday night. I was trying
I
to
just saw my
do,
message.
sorry, Barry, did you say something? Okay, sorry. I'm okay. I'll just go back to wow, there's quite a few questions. So what might go wrong? Yeah, if your mesh is poor, your simulations won't run. This actually happened to me yesterday. I was trying to do I was trying to get a mesh done. I did get a mesh, but it was not good enough quality, and the simulations didn't run. So I had to redo it this morning. So some major softwares that I can recommend for CFD. I personally have the most experience in using ANSYS. ANSYS is one I would, or ANSYS Fluent is the one I would recommend most because of my experience. Star CCM Plus is another software. OpenFOAM is a free software where the first two are commercial, so you have to pay for them. OpenFOAM is a free one. What you pay for is in your time and effort. But there are some courses you can get paid, pay and enroll to understand how to use OpenFOAM. COMSOL, there are quite a few other softwares. COMSOL is another one, and so on. ANSYS, I worked in ANSYS or ANSYS affiliated organizations for about 8 years. So it is one of the biggest simulation software companies, and um, it is try and there's a big research arm trying to ensure that the software is um, ahead of the curve in terms of modeling complex problems. Um, and then what requirements for a CFD engineer to learn about machine learning and artificial intelligence? Right now, that's a nice to have. Um, right, the typical methodology for setting up a CFD simulation doesn't require any machine learning or artificial intelligence at the moment, but that might change in 5 years' time. So if you are familiar with machine learning and artificial learning intelligence techniques, it'll definitely be a plus. Um, what are misconceptions uh, I had when starting my career about CFD? I didn't really think about that way. Um, it's it's just something that happened naturally. My passion was aerospace engineering, and my research was also in aerospace engineering. But then, depending on which country you are in, the level of research you can do or in aerospace engineering may not be the same, and that led me to uh, try studying abroad. And after that study, I got a opportunity to work in ANSYS, and that's how I just moved. So I didn't really have any conceptions or misconceptions. So you just allow, my advice would be, you try to do the best you do in whatever you have learned, and if you and then you'll start seeing doors open. If you are good at what you do, somebody would be willing to pay you what you want to be paid. um, and then, yeah, I've answered, do you is it necessary to have ML and AI knowledge? Not right now, but in 5 years maybe. CFD can help manufacturing by visualizing flow fields, identifying problem areas, and then applying solutions. So, for example, CFD is widely used in the Formula One industry, and based on the CFD simulation, you generate the shape of the race car, and then manufacture it. So, similarly, you can use it in other industries. Um, and then, okay, I'm just checking if there are any other questions. Type of system requirements. A typical desktop will be okay for using like the student version of ANSYS. It's a free version. You can use up to 1 million cells. You can still do only simple problems. You can't do any commercial simulations. If you want to do commercial simulations involving tens of millions of cells, you need at least 36 to 128 core machine, which would cost anywhere between uh, ten to $15,000. It might even go up to $20,000 if you add in a very good graphics card. So unless you are asking this as an organization, I think that kind of cost is prohibitive to most people. DNS, I think we are still about 100 years away, unless there can be a breakthrough in quantum computing. for doing a DNS of an aircraft, you need a quantum computer to get that, I think. Interpreting large results from CFD, you have to look at simpler test cases to validate your setup. And if your setup is validated, you change the geometry, make it more complex, and then you'll have more confidence in that the results of your CFD make physical sense. So I would always say have a benchmark or a test problem on which you are validating your CFD. Laptop system, again, if you want to use ANSYS student version for 1 million cell meshes, you can use any AMD or Intel system with about 16 gig of RAM, i7 or Ryzen, like 8 cores, 6 to 8 cores of processors, and maybe a graphics card with 6 to 8 GB of VRAM, graphics card RAM. So that'll all, you can get it for about 1,500 to 1,500 US dollars. I'm not sure which. You can probably convert that into your own currency and look for options. Finding an opportunity as a CFD engineer in aerospace, I guess it depends on the country you're in. It is, if you're an American, you have a bigger pool of opportunities you can choose from than if you're in a third world country. It's just the nature of how aerospace is. So I would say if you really want a career in aerospace, maybe look at applying for universities abroad. Even then, you'll need some permanent residency requirements to actually get into the aerospace field. So it's going to take a long time, and by that time you might find something more interesting. So data was, we got how the velocity of the train changes, and along with the geometry, the velocity of the train changes with time, and then we did a CFD simulation to show the movement of the train into the building, or into the railway, underground railway station. I think we are already 5 minutes over time. If Barry is happy, I think we can close this here. And I think Barry would be able to follow up with any other questions.
All right. Thanks very much, Vijay. Thanks, everyone. So I see you sending your emails. In fact, if you signed up or registered for this webinar, so our team will be able to send the certificate to your email. But before we carry on to that, I just want to share some of the courses that were being covered in this program. So you'll see a professional certificate of competency in digital twins and simulation monitoring, our graduate certificate in mechanical engineering, graduate diploma as well, advanced diploma in mechanical engineering, bachelor of science, and our master's program. So those are some of the programs that we are offering, which were part of this discussion. And then just for more information in terms of upcoming courses, so if you can just maybe go on our website, eit.edu.au, you should be able to read more and see some of our upcoming courses or programs. And then, yes, as we've mentioned, in terms of certificate of attendance, so what you need to do is you need to scan the QR code, and we should be able to send you the certificate of attendance. So you need to ensure that you complete the form, and then thereafter we will send you the copy of this certificate within at least 3 to 4 working days. So 30th of September, that's the cutoff date for claiming the certificate of attendance. I'll just give some times. If you can just scan the QR code. For those who are not able to scan the QR code, I will put the link in here so you are able to follow the link. Just a sec. One moment, please. Yes, so you can use this link in order to request a certificate of attendance. Just a second. Why is it not copying? But let's see. You can follow that link in order to request the certificate, or you can use the QR code. And then, yes, for more information, you can always go on our website, eat.edu.au, just to see some of our programs and also some of our upcoming webinar sessions. You can go and register. And then lastly, we would love to hear your feedback. We would love to hear some of your comments. So if you have something to share with us, please go to webinars@eit.edu.au and send us your email with your feedback, and we would love to hear some of your comments and feedback. Otherwise, thanks very much, everyone. Vijay, thanks very much for your presentation. And yeah, we shall see everyone in the next webinar. Just go to EIT for more details. Thanks very much.
Thank you, Barry. Thank you so much.
Yes, everyone.